I am pleased to introduce, in minimalist fashion, John, Jason, and Meet of Zorro, and they'll tell you more about them, Zorro, and hopefully something very interesting about their journey from traditional keywords onward.
All right, thank you so much, David. It's great to be here today. My name is John Vivers. I am the product manager for search at Zorro, and we're here to talk to you about our journey through the search landscape over the last 12 months or so. So I'm going to start by showing our agenda for today. So we're going to tell you a little bit about Zorro, what it is and what we do, and kind of where we started. So we started with a third-party search provider, and we took the decision to take search in-house, and that meant we had to build, search from scratch and create a team to do that, and kind of the challenges that we faced, how we overcame them, and some of the key takeaways from that lesson as we go through that journey. So let's start by talking just very quickly about Zorro. Zorro.com is a tools, parts, and supplies e-commerce website for your business. So our primary customer is the B2B customer, the mechanic, the electrician, the plumber, and these people need to purchase things to be able to complete tasks around their business. You might be an office manager, you may need to purchase trash bags, for example. So we're going to sell that. And as a result, our goal is to be what our parent company calls an endless aisle. So we want to have anything that you could possibly need in order to run your business. And so we have about 14 million SKUs in our product catalog across 30 verticals. And we've just got a lot of growth going on. So even 2 or 3 years ago, I think we were at 8 million SKUs. A year or two from now, we'll be at 20 million SKUs. From a revenue and traffic perspective, we're growing in the double digits every year. So one of our biggest challenges is just to kind of keep up with that growth and develop strategies that allow us to continue to execute as everything around us is changing. So first thing that we want to address is kind of why we took search in-house. And up until, January 2024, our search was powered by a third-party search provider. We felt that it was very important for us as a company to own our customer data and to own the experiences on the website. And we felt that we were struggling to deliver the types of relevancy that we wanted to deliver with a third-party provider. We didn't have a lot of ability to innovate within the search space. And we felt that our data was being locked away. We wanted to be able to use that search data in other areas of our business, in recommendations, in customer retention, in SEM. How can we create a holistic journey for our customers? So that kind of drove us to the idea of let's create this in-house solution. Another thing that kind of made us think about this was that there really aren't that many providers that scale to 14, 15, 20 million products. So if you're building a third-party solution, most retailers are, 100,000 SKUs or less. So we had a kind of a unique challenge that we couldn't really find a marketplace fit for. And we felt that there was probably some cost savings in doing this too. So where do we start? We've got kind of 4 circles here. This will keep repeating throughout the presentation, but we started with data collection. When we were working with the third party, really the function that our teams had with search was just preparing that product data and publishing it to this third-party provider, installing their tag on our website, and then letting them run the experience. We very quickly realized that if we were going to do search, we needed to understand the customer journey. We needed to do more than just prepare the products for search. We needed to understand those behavioral signals. So as I mentioned, I'm a product manager. I have a very basic understanding of this stuff, but this is an ideal journey, right? Somebody does a search, they go to the product, they add that product to cart, and they make a purchase. But that's not realistic. Customers are going backwards and forwards across all phases of these journey. They're repeating, they're looping around, they're exiting. Your customer journey within your logs is going to be a mess. And there are far more pages than just search, products, add to cart, and purchase. But a common theme across all search platforms really is that these are the key interaction points that you want to focus on when you're trying to understand the search journey. And then there's certain very specific interactions that you want to focus on more. So when people repeat searches, or when people get from search to a product and then look at other products. And of course, whenever customers exit this journey, we want to understand when that's happening and hopefully why that's happening. So we can distill the insights down to looking at a few key data points and a few key iterations within the customer's journey to start drawing some insights out of that data. Secondly, you want to be able to segment your queries. What we discovered as we looked at our query logs was that there are really about 3 key behaviors that were happening on our search platform. So firstly, people were using keywords to search for products, right? That's an obvious one. I've come to the website, I search for generator, I want to see some generators. We also had people searching using identifiers, so manufacturer part numbers, UPCs, and ideally our own internal Zoro SKU numbers. Those customers knew exactly what they were looking for. They could describe it in very clear language, and those were relatively easy searches to fulfill. And finally, browse traffic. You have customers that are going through the taxonomy, browsing the brand pages and trying to figure out where they're going to find the products within the taxonomy that they're looking at. But even looking at those broad brushstrokes, we want to be able to break that down further. So taking the keyword search for an example, if somebody is searching for the word generator, they may be very early in their shopping journey. They know they need a generator, but they may not know an awful lot about that generator. As they start to use more terms to describe that, they're getting a little bit more specific about what they're looking for. And we've got a much higher level of intent. So we want to break down these journeys, not just by type of search, but by the intent within the search, whether they're head terms, tail terms. And we want to look at different metrics. What are our result counts in each of these? How often do we return 0 results? What's our conversion rate? This gives us a map and a common language that we can talk across product, engineering, UI, UX, and identify areas within our customer search journeys that we want to optimize for, that we feel that we can improve, and that we want to make sure we're fulfilling a need on. And so that kind of led us into, strangely enough, offline testing. Before we could move from our third-party provider to our own internal search engine, we wanted to be sure that our search was going to be reasonable. It was going to return good results and be equivalent to what we had already. So the breakdown of keywords really allowed us to create the judgment sets that allowed us to start doing that offline testing process. And what we wanted to make sure is that we have directional consistency between our offline testing and our online testing. So our judgment sets, our traffic splits kind of mirror what we're seeing within our query logs. We want to make sure that our offline testing is diagnostic, so it allows us to actually figure out where we need to make improvements. It's got to be repeatable and it's got to be observable. We've got to be able to actually get into the details and understand what's happening. And so with that, I'm going to pass over to Meet, who's going to talk about how we built our offline testing platform.
Sorry, I needed to get it all the way down. Oops. Okay, thanks, John, for such a beautiful introduction and context. So just a little bit about me. I am Meet. I'm a senior search relevance engineer at Zoro. Well, I work on search. So based on what John mentioned on the left here, this is a stack that we have for our offline testing. I wouldn't be diving much into the details because there are a variety of systems available. But to achieve what John basically said, the 4 requirements of offline testing, we need to take care about careful nuances in the ingredients for offline testing. So the first ingredient is judgments. Now we capture judgments in a variety of different methods. Number 1, click ratings. Basically, for a given query, what are the products that users have clicked on, and then use algorithms such as STBN and some nuances to it, like pooled calibrated STBN and stuff have worked for us. Getting human annotations by subject matter experts. Synthetic data is essentially also human generated data, but that's by us, like We have a specific problems that are reported by customers, which generate synthetic data that we want to test upon. And recently, we have also started leveraging using LLMs as judges, and there has been lots of talks about it during this last few days. The nuance that I was mentioning about is, in practice, what we have found out is click ratings have sort of most closely replicated about the behaviors that we see in production, because they are essentially crowdsourced and sort of, captures the true user behavior that are across mindsets, cultures, thought processes, and in different phases of their journey. Secondly, judgment sets. Now, anyone can build judgment sets for our offline testing. Someone even with rudimentary knowledge of SQL could build judgment sets. We have judgment sets for particular stratas like keywords, identifiers, browse, etc., etc. One good nuance out there is, we have created a mixed judgment set. So what a mixed judgment set is, basically take a proportion volume of your stratas, what you have online in online traffic, and replicate the same proportion volume on your offline traffic. And we have found out that that sort of almost very closely replicates to what we would be seeing in online A/B testing. Obviously, evaluation metrics are pretty standard. And before I dive into evaluation views, I would say we offline test extensively. Like just in this last 2 weeks, we have run about 72 experiments across 550,000 queries and across 19 million query product data. And so these are the views that we have sort of to achieve the other capability that John mentioned about diagnostic capabilities, like a bigger picture. We always want to sort of compare two different models at a broad level, like what are the average results, what are the zero results, what is corresponding NDCG and stuff. Now, whenever we have sort of a new model that we want to push, there are always a set of queries that improve and set of queries that degrade. So for those kind of queries, you want to have a sort of a side-by-side view to basically figure out what is really happening. And once you sort of determine the queries which are essentially upgrading or degrading, or basically something's not looking right, you basically go into the fine-grained views like explanations, or go to your LTR models, Shapley values, and all those kind of stuff to figure out why that is truly happening, and basically fix those things. Now, why this has been an impactful portion of our journey is that this allows us to have models or winning models deployed rapidly, without a lot of A/B testing. Deep dive diagnostics like this allows us to pinpoint specific portions where the model is not doing good and fix it. It sort of allows us to isolate different problems. You could create different judgment sets for different problems and tackle them separately. And they're less expensive than A/B testing. Obviously, we A/B test all of the changes, but sort of running 72 different experiments even before finalizing one model for A/B testing, that's a big win. So going to the second phase of our journey, traditional keyword search. It's pretty standard, lexical matching. We were using BM25 title scores. I wouldn't dive much into the detail. And we were using product popularity scores. So for all of them, in e-commerce industry, they would have a variety of metrics they would track. Revenue, customer lead time, is this a fast shipping or not? What's the geolocation as compared to the customer, etc., etc., etc. There could be 25, 30 metrics. And we had developed one static metrics based on all of these called the product popularity metric, and we used to statically load them up in the index and use it in ranking. And it used to work fairly well for us, but there are more nuances to it that we will come to later. What it did well, as John was mentioning, great part of our searches that convert were SKU numbers and part numbers searches, and this basically worked on it. It basically had high return on effort, and this by itself was sufficient enough. I mean, obviously there was a lot of tweaks to analyzers and stuff, but was sufficient enough to get us off the third-party search provider. Now, where it fell short, and now we are gonna dive into our journey, that it did not have any synonym or semantic understanding. For example, if a while ago you would have searched for hex keys or island branch on our website, though both of them mean the same thing, they would have shown different results. It did not learn from user behavior. The results were static. What do I mean by that is always based on product popularity, the same product would always hold the same place despite of previous user interactions. And typos and zero results were a big problem on our website. So we started doing some AI enhancement and semantic intent understanding. Again, we started simple. Just take all the queries across your log, find out all the queries that differ by a space, and make them as synonyms. Now, it might sound such a dumb thing to do, but it had a huge impact for us. For example, many people might know Packout, which is sort of a Milwaukee's product line or a sub-brand. And there were customers who were typing pack space out on our website, and there are many such examples. They either used to get irrelevant result on such kind of searches or null searches. So this resolved many of those cases. And then, within a session, try to look for subsequent queries which differ in only one character. So for example, here someone is typing rigid, and basically what they're intending for is brand rigid. And so this kind of fixes this. Now, obviously, a question arises like, why not use fuzziness rather than synonyms? Because fuzziness sort of tend to be expansive in nature, and we didn't want it to introduce new results in there. So we rather stick with synonyms, and fuzziness also has more latency as compared to this approach. So then we moved to more advanced models for user behavior, because at this juncture, even it lacked semantic understanding. Like, it could not say that ln branch and hex keys are essentially the same thing. So next approach was basically take user queries and the set of products that they add to cart. Now we basically calculate the synonyms based on the foreground set, background set mechanism, where the products that have been added to cart are treated as a foreground set. We basically take co-occurrence of terms in the foreground set and sort of contrast that with all the things that are occurring in the background set. That sort of helps remove stop words. So for example, in foreground set, sawzall and the would also have co-occurred, and sawzall and reciprocating saw would also have co-occurred. But basically when we check the background set, the occurs across every document, so there is very little information gained there. But reciprocating saw doesn't occur everywhere. So that's some semantic meaning there between sawzall and reciprocating saw. So that's one method that we use to generate synonyms. And on top of that, we also took co-add to cart. Like for example, for two different queries, if same product were added to cart. So here, foreground set was all the set of products that were added to cart for those two queries, versus background set being all of those products that were not added to cart for both the queries, either for one of them. But this required a lot of user data, or we need to filter on a lot of data to achieve some significance. And this allowed us to achieve many different synonyms. Now, one might ask, like, why go for cart query? Why not click products? Where click products sort of contain a lot of noise in our case and sort of tended to make it over expansive. So we found the best results for us was to use add to cart, which is more stronger signal, because someone was just mentioning in previous talk that users tend to click a lot of products in e-commerce settings, and that was a problem for us. And one of the recent approaches that we have done, and probably doesn't require much explanation at all, just take user query, add to cart data, obviously put it into LLM. This is obviously not the prompt that we use. It's a little more than this, but it also gives us lots of synonyms like shipping boxes and corrugated boxes. This search occurs across our website a lot of time. Now, this is a self-looped system which sort of keeps on adding new synonyms. Maybe it might be adding new synonyms while I'm talking here. And there are about 11,000 synonyms we have discovered through this. It has the initial A/B testing had made us discover that we reduce our zero result rate by 40%, and there were huge gains in conversion due to this. And with this, I would like to invite upon my lead data scientist, Jason, to sort of talk us through more nuanced models and hybrid search models and so on.
Thank you so much, Meet. Hi, I'm Jason Taylor, lead data scientist at Zorro. How's everyone doing, Haystack? So things are going to get a little bit more data sciencey from here on out. I'm here to talk about one of our first model or enrichment models that we built to try and capitalize on the fact that we have pretty sparse data, and when we do capture data, we want to make sure that we can extract as much value out of it as we can. So in this particular case, we built a set of term enrichment models, or term association models. So essentially what these models do is try to, for each one of our products in our catalog, identify which queries were most successful for those particular products and which ones were least. So really we want to use this to bootstrap future success and allow ourselves to kind of put our thumb on the scale and say, these products were successful for these queries in the past, so we want to boost those products up, and these products were unsuccessful for these queries in the past. So to give a motivating example, because this might not be necessarily clear, so we have an number 832 machine screw here. This is actually you generally aren't thinking of one of these when you're just shopping for screws to build your deck. This has a fairly specialized application. So when people search for this, they tend to be very specific. They tend to look for an 832 machine screw. When they're just browsing, for example, entering a fairly expansive query for screws, they don't tend to pick this one. So it's very important for us to learn that, because it allows us, as we get more behavioral data, as we see, as more of our catalog gets viewed by our customers, we get better and better at nailing this particular ranking aspect. Okay, I'm going to hand it back off to John to talk about typeahead.
Thanks, Jason. So as we were getting more deep into the behavioral data, we started to create these keyword product associations, and we quickly realized that these keywords that are successful for the products are actually the keywords that we want our customers to search on. So we took that information and we used it to build our typeahead index, and understood that you have different levels of intent, but when customers start typing in GEN on our site, they're looking for generators. But ideally, we want them to specify if it's a portable generator or an inverter generator. And so our typeahead index became an output of our term association models. It gave us guarantee that the terms that we put into typeahead were terms that would convert going forwards. It also allowed us to create related searches whereby we can start to prompt the customer for a little bit more specificity. So if they're looking for the deck screw, well, we kind of want to know what size of deck screw that is. We're much more likely to be able to convert on those terms than we are on other terms. So again, just kind of building on the work that happened before for the term association models to build up the keyword index and reuse it in other areas. From here, we started to think, okay, what can we do to expand and generalize this? At this point, we were just kind of using our user behavior to kind of reflect information back to the customer. But we wanted to try and get ahead of that and generalize that. And again, I'm going to pass back to Jason to talk about.
All right. So in keeping with the theme of increasing generality, as John alluded to, so a kind of a specialization on our previous term association model, and getting further and further toward more general type queries. One of the things that we want to find is when somebody enters a search query, what are some attributes of products that might help us narrow things down? We have a very expansive catalog. We have a lot of lexical overlap within that catalog. So sometimes it helps us to try and break down the problem into composite parts. And this really does help us with query understanding. So we trained a couple of transformer models. We want to be able to leverage attention here so we can get some of those semantics into these models. So we just use BERT for this. Primarily launched with two models, one in particular to predict brand, which is one of our most significant product index features, and also to predict category. So we can see here from this example of searching for safety glasses, our predicted categories, there's a little bit more lexical overlap, obviously. The first category is identical. But we can see sort of within these two classes here, that there's not much lexical overlap, but there is a lot of potentially a lot of semantic overlap. So we are using these models currently to possibly to enrich our queries, but also to propagate some of these forward so that we can create smart facets for our user experience. Okay, so moving on to ranking. Why does this matter to us? We have to put things in order. So. But in particular, I don't know if you've got kind of gathered from the theme that we have a lot of data on our products, and lexical search tends to be a little bit less reliable for us due to the size of our catalog. So one of the things that we want to be able to do is leverage that deep well of product information and product knowledge to do ranking. So initially, we were trying to do this with, and I should back up here for a second. We do have a ton of these signals, and often, and all of them are quite strong. All of them are quite useful. So initially, we were putting these in as rank features in a traditional hybrid query plan. Now, the issue with that is our catalog changes fairly often. We are growing really fast. And so as a result, there's a lot of shift under the hood. And whenever we want to add a new feature, we have to rebalance, we have to retune, etc. So that was unsustainable and unscalable for us. So we switched over to learning to rank. So that gives us the interpretability and explainability of using kind of traditional rank features. And it gives us a greater deal of control over how we do our ranking. So we've obviously trained this on the click model targets that Meet was talking about earlier. We include some lexical and some query document features. A lot of this is document-specific features. We can see these sort of in our Shapley values on the left here. And we retrain this continuously due to the fact that our catalog and our traffic mix changes quite a bit. And so our impact here was we had a very significant lift in click-through rate and engagement for our top-ranked results. So that was a big win. And last but not least, in terms of at least my slides, we added vector search in the mix. So one of the things that we kind of keep harping on is that we have a lot of lexical overlap in our catalog. Another thing that Meet had pointed out earlier is that we address this using synonyms, but building out synonyms doesn't scale. It has a great deal of noisiness, and so in order to avoid having to go the manual route, we decided to leverage KNN in both in retrieval and as a potential ranking concern. So, to kind of give an example here, I mean, we have a lot of these, similar conditions where, most people who are looking for example, we have a hex head cap screw here, which is again a specialized type of bolt. Most people are just looking for a bolt there, but there's a whole bunch of different types of bolts. So getting a little extra nudge in the appropriate direction using semantics will help us, kind of resolve some of these harder queries. And we can use those in concert with our other product-based features in order to get the right answer. So how we're using here, we're just using a basic bi-encoder configuration. We're embedding our queries and our product representations into the same space using ANN search, and then we're propagating that forward within hybrid search and also as a KNN feature. Okay. And as a result here, this is pretty dramatically increased recall and relevance for our vague and our long tail queries, and helped us kind of avoid manual synonyms for a lot of our problem cases. All right, I'm going to hand it off to me to talk about LLMs.
Yeah, probably this just builds on one of the questions that was asked during last talk about what to do when we don't have good product data or product data is not being provided. So we have this case extensively with Zoro where suppliers don't provide all the good data. Merchandisers work very hard with suppliers, but then suppliers are busy in their own thing. They don't respond very well. And so ultimately what it boils down to us as a search team is, we believe that better data leads to better search relevance. So for example, this is just one of the example of the kind of titles that suppliers provide us with. Like, I don't know what even left side means, GP, MTR, split PH, ODP. Probably they might have aimed it to sell to a robot who knows everything about whatever this is. But we started leveraging LLMs to sort of enrich our title and description data. And it gave us very good results. Like, it sort of regenerated this kind of titles into what you see on the right. This is just one of the examples from all of the product data that we have enriched. Half HP, general purpose, motor, split phase, open drift proof, whatever, and which is more likely to be searched. Another problem that we had with our data is Again, suppliers are very bad at providing attributes data. Now, attributes, sort of as John mentioned, like at initial phases of the journey, customers type in broader keyword term for discovery, but they ultimately then want to narrow down to whatever their needs are. And especially if they land on a category page, brand page, or any of the catalog page, extensively they want to rely on filters to find out the products that they are looking for. And we had this problem where our brand and browse pages were performing very bad because required attributes weren't there. But if we see that these attributes are indeed present in title and description, so we started leveraging LLMs to sort of enrich this attributes data. So for example, on the left is what is provided to us by the manufacturer, which is nothing. And on the right, it's something that's extracted from the title for this one particular product. Now, this in itself, in our initial A/B testing across few categories, drove 250 basis point increase in facet usage for those pages. Now, I agree, people might argue that facet usage aren't everything, but at least it indicates one signal that now at least customers are finding useful facets on that particular page that they might be wanting to use. And the title changes allowed us to discover products that previously weren't discoverable because of their vague titles. So this was the impact that it had led for us. And so we are still on this journey and continuing our progress from here. So I'll hand it over to John to sort of conclude, or not so much conclude, or say continuation of our journey and key lessons that we have learned from that.
Thanks, Meet. Okay, so what have we learned from our year? I think a lot of what we've said today has probably been covered in a lot of other talks, but we thought it might be interesting for you to see how we put some of these things into practice within our e-commerce environment. But yep, over the last 12 months since we launched our own internal search, a few key takeaways really stand out. Number one, bot traffic distorts everything. So it's great to collect your behavioral data, but if you are an e-commerce site, you're probably getting crawled all of the time, and you want to be able to disambiguate those signals and make sure that the information you're feeding to your models is the true customer interactions and not some bot scraping your site. Simplify your stack. We started off creating some fairly complex ETL processes, some fairly complex query pre-parsers, etc. And we discovered we were spending more time on infrastructure than we were on relevancy. And we realized that what we wanted to do is ensure that we could focus our team's effort on search relevancy. And so we tried to simplify as much as we could to give us more time to focus on the things that matter, the things that drive those impact statements. Quick wins matter. So I think some of the examples that we gave of, mine your queries and look for the stuff that differs by just a space, it's a very, very simple thing to implement, but it's extremely effective in dealing with these gaps in language between the customer's data and the vendor supplied data. And it also allows you to build upon a solid base. So those simple solutions become training inputs for your future models. And it allows everybody on the team to talk the same language and understand exactly what it is that we're trying to solve. By having those simple things that everybody can get behind, you can quickly move up the maturity level and develop much more complex models and actually be able to backtest those models against your simple starting point. Offline testing is a superpower. I think Meet mentioned we had 72 experiments in the last couple of weeks here. I was in a workshop here on Tuesday, and I think we ran 62 experiments in a half an hour to try and understand how to weight lexical and KNN searches together, weight those scoring together. Your ability to execute these offline tests is incredibly important, not just to ensure that you're pushing candidates that are likely to win A/B tests to an A/B test, but also to ensure that your team is on the same page and that everybody is talking about the same thing, and that you're talking in facts, that you have tests, you have data to back up your positions. And I think in the previous test, one of the product managers spoke about that need to back up what you're doing with data. don't overly rely on those offline tests. Human testing is extremely expensive to get to. Your own internal data can be quite challenging to pull together. So most of the time when we're working on offline tests, we're working on click models to generate those judgment sets. And customers just simply can't click on the things that they can't see. So you're going to have a gap in your knowledge. And if you're optimizing towards your click model, you're optimizing towards your existing search implementation. That's why it's so important to have a reason for your model change. I am changing this model to do this, so that when you see that decline in NDCG or that increase in unrated documents, you can go in there and say, well, is that because of something that I deliberately did? And is that the outcome I wanted to see? In which case, I'm happy I can move forwards, even though my offline NDCG numbers are a little less than what my current model is saying. And then lastly, but not least, test absolutely everything. If it is going to touch the customer, it must be tested. We had a number of tests that failed, not because our algorithms weren't right, not because our hypotheses weren't right, but because there was a small error in our implementation, and actually some number of searches were failing, or something was running a little bit slower, or something wasn't just working quite right. We would never have caught that if we hadn't have done that A/B test. And so we need to, that's something that we simply won't compromise on, is everything that is eventually going to touch, everything that a customer will see will go through an A/B test. And that's it. Thank you for giving us your time this afternoon. And it's been a heck of a 12 months for us, but we wanted to kind of explain how we went from having third party running our search to having a AI-powered search using hybrid search and LTR, semantic expansion in 12 months. And so, thank you.
Thank you very much. And before we go to questions, I'd like to apologize to our online viewers. The schedule published had an extra 15 minutes allocated to the previous session, so we actually started early. So you're going to have to do it again.
All right.
So that they can have those 15 minutes back. The finals talk of the day will start at the published time. So there will be a little longer between the end of this one and the last talk. Are there questions? Way up high. While I'm going way up high. No. What click models have you had success with? Ryan would like to know that.
Do you want to take that, mate?
Yeah. So obviously, first one we started with was, so we started rudimentary with simply Bayesian models, but then that sort of has a bias towards low impression, low click models. So I think there's this other books also have literatures about SDBN. So we also went with SDBN, and we did some nuanced version to it where we pooled and calibrated what you could say a train set and a test set to sort of calibrate the learnings that we are learning. And that's what we are using right now. But again, the suggestion would be SDBN is something that's prevailingly available across literature. Just start with that. Then, keep on analyzing this. You might figure out the downsides or the results that are not looking good. And maybe you might find out other methods on improvising upon that based on your own use cases as well.
One note on that is we did also try out cascade models and didn't really see much of a lift in performance.
I have two questions. I'll just compress them into one question. Okay, 1.5. So how often did you find that the offline tests that you're running, the parameters that you learn for tuning that translates well to online? And then the second piece is, you guys meant ANN, right? Because you can't do KNN over 15 million products in that slide.
Yes, we meant ANN.
Okay.
I apologize. And actually, one other thing was that we're actually using the KNN search as a feature within our LTR algorithm. So there was some talks about RRF and then using normalized scores to merge your BM25 and your traditional your semantic similarity scores together. What we found was that neither of those were really satisfactory to us, because we wanted to get those document features in there too, those popularity scores, the review counts, the sales data, and we actually found that LTR was a solution for us, where we could have BM25 features in our re-ranker, we could have the semantic features in the re-ranker, we could actually have those business features in the re-ranker too. So that was a kind of a key takeaway for us. In terms of your other question, how often did our offline tests match online performance? Was that
so
the?
like if you arrive on a set of parameters or a group of models for offline,
Mm-hmm.
do you see them winning online as well, right? As often as you would see it winning offline?
Generally, we would, but I would have to say that we very rarely would win offline. Because of that bias in the click models that we were using. You don't have judgments for things that you haven't seen. You change your model, you're bringing new products into the result set that simply haven't been seen before for that query. But directionally, we would be very confident that things were going to win. And that's one of the reasons that we had other measurements apart from NDCG. So when we were changing a model, for example, hard to call it a model, but the work that we did around synonyms, what were we trying to do there? We were trying to reduce that null search rate. So our NDCG scores actually went down because we brought these new results in. But the number of 0 results that were being returned on our offline testing also went down. So we were able to say, yeah, we've done what we expected to do here. This decline in NDCG is acceptable. Let's push it forwards to an offline test. So I actually can't think of a single time where we actually had an NDCG win offline. So I was always trying to get that close and then take it to the online test once we knew that what we were targeting was indeed fixed.
So Jeff asks, is there any human oversight before LLM-generated synonyms go into production?
Actually, very, very little. There was some cursory oversight, and I think this is one of the reasons that we're so lucky in this search space. And the previous speakers talked to this as well. We don't actually need to show the customer the data that we're generating from the LLM. What we need to know is that it's an effective signal for us within search ranking. So not that we can play fast and loose with this data, but because it is not customer-facing data, it is data that we're collecting to improve our knowledge of search. We could actually move extremely fast, and we didn't have those constraints around human in the loop that you would have if you were rewriting a product name for a product page or a description for a product page, which a customer is going to make a purchase on. So even in the case of synonyms, we were actually able to move pretty fast and really do human in the loop sampling rather than every single synonym being checked. Yeah.
Let me just add a point here. So for our LLM generated product data enrichment, that actually does undergo fairly rigorous human review because of the criticality of it, and that stuff is going up on the site, so we do actually have to white glove it. So
Alexandra asks, how did you deal with the similar product names that have different dimensions or models, so they are semantically close but not exact match?
Shall I take it? Or you want to take it?
As in, like, can you repeat the question? Like,
how did you deal with similar product names that have different dimensions or models, so they are semantically close but not exact match? So thinking back to your filters for a furnace, they have a width, a height, and a depth.
oh yeah. So nominal filter size is always gonna be rounded off, and about how to normalize. So we have got per category defining attributes, and sort of what our normalized values look like as a part of our prompt. We inject that into the prompt when we generate attributes for that particular categories. And that is how we sort of give hints to LLMs about what are the kind of attributes we generate. Again, I would say that take this with the pinch of salt, that it's not 100% accurate, and that's why it's Jason mentioned that attribute enrichment data does go through human review, but still, I don't have exact number to quote, but I would say approximately ballpark it around 85 to 90% of the generation would still be accurate.
Akanaxa? Oh, I'm sorry, I totally mispronounced this name. How did you deal with noisy historical ATC data while creating synonyms based on common products ATC behavior? I.e. for handsaw query, if users also added hacksaws in the past from past search results shown, they might get considered synonyms for your model input.
Okay.
I mean, the sort of the simplest answer there is applying thresholding. So we need to see a certain number of examples of these cases before they rise above the threshold where we consider them. So that allows us to kind of filter out a little bit of that noise. So that's sort of our biggest method for making sure that we
Threshold is heuristic.
Yeah, and the threshold is heuristic. Yes.
And Jim asks, how far did your NDCG numbers move? What is an acceptable step down in your opinion when you added the synonyms that you spoke of?
Yeah, I mean, in general, our NDCG numbers would be probably within about 5% of our current control. Would be considered acceptable. In terms of how far those numbers moved, it really depended on the change that we were making. So when we introduced KNN, vector search, we saw very, very significant moves in NDCG simply due to the better semantic understanding of the queries and this whole new set of our content that really lexical search had never been able to surface for these queries. And that's really why we have these dashboards that are allowing us to dig into the detail and try and figure out, like, was this a positive move or a negative move? And sometimes we had to go back and, take new outputs and relabel the judgment set so that we could get that insight. But we would see 20% decline in NDCG in that case, and like I say, we generally want to push the NDCG to get as close to the current template as possible for those situations.
Thank you for a great presentation. What you have accomplished in 12 months is absolutely remarkable. My question is around misspellings, handling. I think you mentioned that you have some synonyms to basically handle common misspellings.
Mm-hmm.
The question is, if you get to no result at the end of all the efforts you've put in, do you give up, or have you thought about doing sort of an active spell checking step and get alternative spellings?
Yeah,
Thank you.
Our solution is based around Elasticsearch. Elastic has something called suggesters, and so yes, we would use the suggest API to suggest some alternative search terms that we knew there was content for. That was pretty dumb. I mean, that's just based around term frequencies within your document corpus. So where we could detect a spell check, we wanted to encode that and we wanted to have that precision. But yes, we would fail back to some kind of suggester to provide the customer with alternative search terms. Yeah.
Worth noting also. Worth noting also for that was loud. Worth noting also for very common misspellings, it's often the right move to just encode it because it's cheaper. So, and we do have a lot of, like, rigid was one of our biggest ones. People misspell that one literally all the time. Same with Milwaukee. Milwaukee is one of our most common brands, and no one knows how to spell it. We have, we've seen some pretty creative ones. So sometimes you just want to store those.
I just want to say my favorite one was screwdriver, because about half of our customers would search it as one term and about half of them would search it as two terms. So we looked at our product data, we're like, well, who's right? Is it the two-term people or the one-term people? And about half of the suppliers use two terms and about half of them use one term. So
how do you filter bot clicks from Alexandra?
yeah, that is possibly the biggest challenge that we've come up with, and it's so important to get that right, because the bot traffic just is not indicative, and it's not something that you want to learn on. In the end, we flipped the question on its head, and we said, let's stop trying to identify bots. Let's try and identify humans. And that caused us to perhaps misidentify some humans as bots. But if you think about the behavior of a human on your website, they're going to type something into that search bar. They're not going to type it into the URL, and that's kind of as big of a hint as I can give you there. The bots are kind of crawling URLs, whereas the customers are going to have some other interactions, some other events that are happening prior to that in their search, and that's what we keyed in on. And that's not to say that customers won't directly land on your search pages. Anything you do, there's always a trade-off. But the key point for us was, don't try to identify the bot, try to identify the human. And that made things a lot easier.
Bilal asks, you mentioned that fuzziness is expensive. Do you only use LLM-generated terms for this purpose?
As in, I think both questions are sort of, I don't find the correlation between them, but fuzziness is expensive as in, like, if you want to introduce fuzziness just to correct one character mistakes in the spelling, but that would sort of scale to all the searches. So for example, you just want to correct rigid to rigid, but if you apply fuzziness of one character, then I don't have a correct example on top of my head, but it might also spell correct a correct search term to something else as well. And that's why it increases the recall, and also, I mean, not recall precisely, but number of results we get back. And that's why it increases latency. But yeah, LLMs are sort of unrelated. LLMs are more on the semantic realm, where semantically with the statistical methods, we are able to generate synonyms only for the user behavior data that we have seen. But let's say certain products are not discoverable by the user because we don't have semantic synonyms for that particular thing, then we'll never have users who would interact with that. So how do you sort of solve problems for those kind of things? So that is where LLMs come into picture, that even when one small signal can sort of spark it, versus if you want to use statistical methods, you would need a lot more signal to gain some confidence about if this should be included in the synonym set or not.
And now, to ensure that we actually get back on our schedule and you won't finish until 3:30, I give you from Prathmesh. Did you fine-tune your embedding language models specifically for domain-specific vector search, or are you leveraging models without additional training? Could you also share the rationale behind your approach? And I will see you all at dinner.
Okay. Well, fortunately, we got a very simple answer for this, and that answer is we did not fine-tune our embedding space model for our domain. For a couple of reasons. I think our most salient reason is that we have a very broad product catalog, and this early in our journey, we were not confident that fine-tuning was going to be. We thought that might be premature. Now, I'm not at liberty to share our current roadmap, but needless to say, we are looking into more sophisticated models, more sophisticated embedding spaces, two-tower models, things like that. That will help us converge and will help us perhaps fine-tune a domain-specific model or train our own domain-specific model. But really, our sort of initial motivation was we weren't really sure enough about the space yet, so we really didn't want to start, applying sophistication before we tested out a basic version. In keeping with the principles that John sort of indicated before, try the simple thing first, and so that we did, and ended up working well enough for us that we were able to push those modifications a little further down the line while our team of 3 worked on other things. So, yeah.
Last chance. Any questions in the room? Let's thank our speakers.